Welcome back to Structural Dynamics course. So, this week in this module we will study undamped forced vibration. So, what is undamped forced vibration or what is forced vibration? So, earlier we had studied that say a structure is there which is set to oscillate by giving initial disturbance. So, structure is oscillating. So, where force is not taken into consideration, only initial displacement or initial velocity is taken into consideration. So, that is called free vibrations. So, now this week we will study about the forced vibration where force is continuously acting on the structure. So, this is called forced vibration. So, we need to take force also into our equation of motion while solving it. So, the outline of this module where we are discussing undamped free vibration is like how to find the solution for undamped free vibration, and we will solve an example problem on that. So, this is general equation of motion or dynamic equilibrium equation. So, in this dynamic equilibrium equation we have three terms, that is inertia term, damping term, stiffness term, as well as externally applied force term. So, these four are there, and inertia, damping and stiffness and externally applied force. And the types of systems are like, if force is not acting then we call it as free vibration, if force is acting we call it as forced vibration, and when damping is not present it is undamped vibrations, and if damping is present it is damped vibration. So, undamped free vibration and damped free vibration. So, these two things we have already discussed, and now in this module let us discuss undamped forced vibrations. So, now how a system and the equation of motion looks like, it is like this. So, mass is there at the roof level and stiffness, that is resisting elements, and damping is not present in the system, and the excitation force which is in the form of sinusoidal excitation with constant force P0. So, that is how it is written, P0 sin omega t. So, omega here is a forcing frequency, it is not natural frequency, do not get confused with natural frequency. Natural frequency is a system property which depends on mass of the structure and stiffness of the structure. Forcing frequency is the frequency at which force is getting applied, say like this, frequency at which force is getting applied is forcing frequency. So, what is going to happen if say force is dynamic and it is acting. So, if you can see this is a cantilever beam, or you can assume this as a diving board of a swimming pool. So, if a person is standing, here, then because of the self weight of the person there will be some deflection, but all of a sudden if person starts moving up and down, up and down, up and down, so what will happen to deflection? Surely it will increase and sometimes it will decrease. So, what happens is a person is coming down, going up, coming down, going up. So, with his knees bend up, down, while knees is bending, so person can go up, down kind of thing, while his foot is resting on the edge of the diving board. So, then motion will take place in this one, which is more than static equilibrium position, and sometimes it is less than static equilibrium position. So, how this dynamics is taking place, that we are going to study in this module. Equation of motion we have set. So, we need to find the solution for this equation of motion. So, what we are going to do is, like in this equation we first divide all the terms by mass. If we divide all the terms by mass, so equation looks like this, u double dot, and k by m is nothing but omega n square, p0 by m and sin omega t. So, this omega is a forcing frequency and omega n is a natural frequency of the system. Now, this is like non-homogeneous differential equation. Homogeneous differential equation means what? Where right hand side is 0. So, this right hand side is non-zero. So, that means we call it as non-homogeneous differential equation, and this is linear differential equation. So, the solution of this one will have two components. So, one is complementary component and second one is particular integral component. So, this complementary component depends on the natural properties of the structure system, and particular integral depends on the force being applied. Now let us evaluate this particular integral and complementary function. So how the particular integral will be? So usually if the forcing frequency or forcing function is sin omega t, so particular integral will also of the form sin omega t with some constant c, which we need to evaluate that constant. So if u is a assumed solution, then let us derive u double dot. So u double dot is 2 times differentiation of this term. So if we differentiate this 2 times, so what happens is like omega cos omega t, and again if we differentiate, it will become minus omega sin omega t multiplied by again omega. So we get minus omega c sin omega t. So let us substitute u and u double dot in the original equation. So if we substitute u and u double dot in the original equation, so this is a u double dot, so this term, and k by m u, so by is equal to p by m sin omega t. So how to solve this one? So the easy method is we need to equate this we need to take common these sign terms and then equate the rest of the thing with the coefficient. As you can see this one, if you rearrange this above equation, we get minus omega square plus omega n square c sin omega t and then sin omega t. So this sin omega t common, so we can take out from this c. From the above equation we get constant c as p naught by m into 1 by minus omega square plus omega n square. Now if we rearrange these terms by taking omega n from this bracket common, so then what happens is omega n square by omega n is equal to 1, and this omega square by omega n square is equal to r. So here we call r is equal to frequency ratio, that is omega by omega n frequency ratio. So then the equation can be rearranged like this. So u particular integral will be p naught by k. So this is c is derived as p naught by k 1 by 1 minus r square into sin omega t. So this is the particular integral. So now we need the full solution. So ut is equal to u0 sin omega t. So this u0 is giving amplitude to us, and then sinusoidal part is sin omega t. So usually there will be some phase in this one, but for undamped vibration, phase will be only when omega is less than omega n, it will vibrate in phase, and omega is greater than omega n, it will be out of phase. So we will discuss about this phase a little while later. So let us concentrate on the amplitude of vibration. So amplitude of vibration, that is u0 is equal to p naught by k. So p naught by k is nothing but static deflection when mass is at rest, static deflection multiplied by this dynamic amplification factor component. So then the total solution will be u is equal to complementary function plus particular integral. So now we need to find out the complementary function also. So this complementary function originally we know from the undamped pre-vibrations case, a cos omega nt plus b sin omega nt together with the particular integral part. So now we need to get rid of a and b constants. So we'll get rid of these a and b constants by using initial conditions, which we already know. So at time t is equal to 0, displacement is u0, at time t is equal to 0, velocity is u dot 0. So at time t is equal to 0, if displacement u is equal to u0, if we substitute that in this one, then u0 will be a, and then at velocity component is, so u dot 0 will get b omega n plus p naught by k omega by 1 minus omega square. So using this we can get b, constant b, as this term, and then if you substitute back in the original equation, so this is a solution of undamped forced vibration. As you can see that if you remove forcing frequency from this one, it will go back to undamped free vibration situation only. Now how it looks like? So it has two components in it. One is like transient component, and second one is steady state component. So if you look at this dark blue line, so dark blue line is showing us the total response, whereas this dotted red line is showing the steady state response. So steady state response continues forever as long as the force is there, and the total response is in addition steady state response plus transient response. Usually when damping is not present, this transient response will continue forever along with the steady state response, but in cases where damping is present, so usually it dies out, something like this. It merges with the steady state response. Now let us look at the overall undamped free vibrations in a nutshell. This is the equation of motion of undamped forced vibrations, and then this is a simplification of that equation, and by solving it we get this as a solution, and the plot is this. Then let us solve the example problem, one problem application of it. Say here I have a problem, a generator of 1 ton weight is placed on a concrete plank of width 500 millimeters and length 2 meters and thickness of 120 millimeters. So, the dimensions of the plank are given, and find the static and dynamic deflection of generator running at 2000 rpm, and use M20 grade concrete for that plank. So, it looks like this. So, it is simply supported, length is 2 meters, and weight of the that motor weight of the generator is 1 ton, and the thickness of the slab is 120 millimeters. So, we are placing this at the center. So, if this is placed at the center, then it will automatically cause the deflection. So, using that we can find the stiffness of the system. So, let us first find the system properties. First, let us find out mass of the plank. So, mass of the plank is 2 meters length multiplied by 0.5 meter width multiplied by 120 mm thickness. So, all these three things is volume, and then this is weight density of concrete. So, we get 3 kilonewton. So, if we convert that into kg, that we get 300 kg as the mass of the system. And then modulus of elasticity of the system according to IS 456, we get 5000 under root FCK, since characteristic strength is given as 20 Newton per mm square. So, we have 5000 under root 20. So, we get 22,361 Newton per millimeter square is modulus of elasticity. Then we find out moment of inertia. So, that is BD cube by 12. So, B width of the plank on the other side, as you can see, this one width of the plank is 500, and then the thickness is this. So, B is that 120 mm thick, BD cube by 12. So, that is 72 into 10 to the power of 6 millimeter power 4. And then stiffness of the plank. So, first we find the stiffness of the plank, K, because it is simply supported. So, 48 EI by L cube. So, substitute all the values, 48 E value as in here, and I value as in here, and then length is a 2000 millimeter. So, we get stiffness as 9.6 into 10 to the power of 3 Newton per millimeter, and that can be rewritten as, if we convert the units, so 9.6 into 10 to the power of 6 Newton per meter. Now, let us find out the natural frequency of the plank. So, natural frequency of the plank depends on the system properties, that is under root K by M. So, K is known value, that is 9.6 into 10 to the power of 6, and mass is 300 kg. So, that gives us 178.9 radians per second. First find out the static deflection. So, static deflection is U static is P naught by K. So, it is something P naught by K is static deflection. So, P is the load of the generator or motor, that is the ton is converted into Newton. So, that is 10 into 10 to the power of 3 divided by K. K is also known to us 9.6 into 10 to the power of 6. So, that gives us 0.001 meter. So, that is equal to 1 millimeter. And then we need to find out the dynamic deflection. So, for that the equation of dynamic deflection is U0, that is amplitude, that is UST into RD. This is amplitude of dynamic deflection. So, use UST into RD. So, UST is nothing but P naught by K, RD is 1 by 1 minus R square, 1 by 1 minus R square. So, if we substitute all these values in this one, we are getting 2.0 2.71 millimeter. So 2.71 millimeter as a dynamic deflection as opposed to 1 millimeter as a static deflection. So that means because of the running of the motor, so deflection is becoming higher because of the running of the motor. But here we need to understand one case when simply supported beam is there, when motor is kept on the center of the beam, motor is running at the operating speed of 2000 rpm. But what happens is, like when you switch on the motor starts, it takes time to go to this operating frequencies or operating rpm. So it starts from say 0 and then 10 rpm, 20 rpm, 30 rpm, like that. Slowly it is going and then reaching 2000 rpm case. So what is going to happen in between this 0 to 2000? So let us discuss that. Now if you look at this one, so in this we will discuss the resonating condition. So resonating condition arises when R becomes 1. So here rpm is 0. So that means it is static. Then omega. So omega is a forcing frequency. The relationship between that rpm and forcing frequency is this. So 2000 rpm. So 2 pi by 60 per minute is there. So 2 pi by 60 into rpm will give us the forcing frequency in terms of radians per second. So exactly that we are calculating. So this is rpm of the machine, this is forcing frequency of the machine, and this R is equal to omega by omega n, and then Rd is calculated using this equation. Rd is calculated using this equation. So if it is at rest, then Rd value is 1. So that means dynamic deflection and static deflection are same. Now when rpm is slowly achieved 100 rpm, then at that time, so forcing frequency is 9.1, and then at that time R is, so this frequency ratio is 0.05, and then Rd is very near to 1. So if you look at this, so if when it is increased to 500, then omega is 45.5, then R has increased, frequency ratio has increased a little bit further, but still it is at 1 only, Rd is 1. That means what, there is not much difference between static deflection and dynamic deflection. So when rpm became 1000, then frequency has become forcing frequency is 91, and then R has become 0.5. So here you can see that there is 30% increase between static deflection and dynamic deflection. In a way you can take Rd as U0 by UST. So that means like what, by how much amount the percentage increase compared to static deflection. So it is 34%. Now when rpm has become 1500, it is 2.39, and when rpm has become 1800, then it is 0.9 is R. Then you can see this became 6 times, and when rpm became 1900, it became 15 times. When rpm became 1950, it became 63 times, and rpm became 90. You can see this, it's very increasing very fast, and suddenly it has dropped here. Suddenly it has dropped. So that means something is happening between R value 0.999 and R value. So just before 1 and just after 1 something is happening. So if we discuss that using the graph, it is something like, on x axis let us take R, and on y axis let us take Rd, which is dynamic amplification factor or ratio of dynamic deflection to static deflection. So when R is say 1, so before R is 1, it is starting from with 1, when R is 0 it is starting from 1, and then slowly it is increasing, gradually it is increasing, and suddenly it is increasing when it is reaching 1, and then after that it is falling down. After that it is falling down. So this is dynamic amplification curve. So if it is exactly equal to 1, this value goes to infinity. This value goes to infinity and then comes back. So what happens is, practically this is not possible. Why? Because if you can look at Rd, dynamic displacement is static displacement multiplied by Rd. So what is static displacement? 1 millimeter only. So then what happens is this 1 millimeter multiplied by this RD. So that means what, 1582 millimeters. So that means length of the plank is 2 meters and the deflection is 1.5 meters. So this is not possible. So what is going to happen is either motor is going to fall outside of the system at the resonating condition, or the plank is going to break. So this tells us the presence of damping, or this tells us the importance of damping to be present in the vibrating system, especially during near the resonating conditions. So here it is in the limit, perfectly in limits of deflection, but when it is nearing the resonating condition, it is deflections are very high and system may break. So damping is very important to be included in the system where vibration are natural, where the frequency of vibration is very close to natural frequency of the system. In summary, so what we have studied in this module, so we have developed equation of motion, and we tried to find the solution of that equation of motion. So solution of equation of motion contains two parts, two components. One is a complementary component which depends on the system parameters, and particular integral which exclusively depends on the applied force. So we found out complementary function as well as particular integral, and then applied it to one example problem and understood the resonating condition also.